As I mentioned, my name is Crystal, and this summer I worked on a project where my mentor and I looked at carbonate nodules from Meade Basin, Kansas, to see if they've undergone any chemical alteration after soil formation. And this project branches off from a larger study where paleontologists at Meade Basin are looking at past climate and environmental conditions and how it may have affected the evolution of rodent fauna. So just a quick visual where Meade Basin is first. Meade Basin is located in southwest Kansas in the Great Plains, and the sections that we collected samples from run along two tributaries. So one here is Cimarron River and the Crooked Creek. And we chose Meade Basin for this study because it's known to have a really good biostratigraphic record of the Miocene and Pleistocene period. So during this period of time, there was a drastic change in climate conditions from a wet and cool climate area to a hot and more dry climate area, and this caused the region to change from a forestry to a more grassland environment. So along with these environmental changes, it affected the ability for certain rodents to survive, and we want to see how they may have impacted them. So how are these factors measured? In past studies, which is part of this larger project, several isotopic analyses were taken of the sediments collected from Meade Basin. So three main isotopic analyses that were taken was the first being delta C13, which helped us have an idea of the organic matter, the abundance of organic matter in the region. Then there was delta O18, which helped us estimate the aridity or the dryness of the soil, which would attribute to soil moisture. And lastly, clumped isotope analyses or just a combination of stable isotope analyses that give us a general idea of the soil temperature during that time period. So with a combination of all these isotopic values, we're able to create an isotopic signature of the Paleosol layers that we're looking at. So here is just a simple diagram of a soil profile. And in layer 1 is our groundwater level, and layer 2 is our vadose zone, or our well-drained area where our soil is forming. And as soil is forming, carbonates are also forming, and coexisting with this are microorganisms, as well as certain climate conditions that the carbonates are able to grow in equilibrium with, and therefore mirroring the type of isotopic values that come from the environmental conditions. So in a way, these carbonate nodules are seen as a fingerprint of the environment they formed in. And then millions of years later, our carbonate Paleosol level has moved down into the groundwater level, and now we have a new layer of sediment in layer 3, labeled as layer 3. And now that the carbonate nodules are in contact with the groundwater, it's beginning to dissolve, recrystallize, or have secondary crystallization patterns, which mimic more of the groundwater isotopic values now. So now there's more fingerprints, and it's harder to tell what was the original fingerprint there. So, so in addition to this, there's also the change in environment from the forestry to grassland area, as well as different climate conditions that also can be seen by traces of isotopic values in the carbonate nodules. So in trying to detect diagenesis in these carbonate nodules, the purpose of my project is to see whether they do have any sign of these alterations, so to see if they can be true reflections of the Paleosols that they originally formed in. And with this information, we were able to interpret these geochemical records to have a better idea of how we can use them. So here's just a couple of pictures of the collection sites that we visited in Meade Basin. So this one to the left is High Banks, I believe, and here's an example of a soil profile that we collect our sediments from increments of 10 to 50 centimeters. And once these samples are collected and have gone through the isotopic analyses, 56 actually of them were gone through isotopic analyses. And from those 56, I looked at 22 of them and made them into thin sections to be prepared for optical analyses. So once the thin sections were made, they were ready for Cathodoluminescence Imaging, or CL imaging. the way that this works is that the sample is placed in the vacuum chamber, as displayed here, and the vacuum chamber helps remove any interfering particles from the CL reading. And the CL electron beam is directed towards the sample, and as this is happening, electrons within the sample are becoming excited, and they're jumping up to a higher state. And as they're coming down to return to ground state, they stop at intermediate levels. And when this happens, they give off energy and visible light, or to us, looks like colors from a range of yellow to dark red. And then we're able to see that back through the microscope. So here's the CL microscope that I used at CU, Boulder. And here is where the sample is placed in the vacuum chamber. And here's the CL electron beam that's shot towards the sample. And here's an example of what we would see. And we also are able to take images in plain light and cross-polarized light to compare to the CL images. So here's an example of a photo in plain light compared to CL light, just to show you guys the distinct differences and why it's so important that we use CL. In picture A on the left here, you can see the variation in color and linings between the white area here, and you kind of can guess that maybe there's some grain size variation, maybe there's some different fabrics going on, but you can't really make that distinction. Unlike in photo A and photo B is under CL imaging, and here is much more distinct of the color variations, and you can have a better idea of the size of the grains from the outlinings here, and also different types of fabrics, like from the difference of this outer darker area and the lighter luminescence of red and orange as you go towards the center. So from what you can see, CL imaging does tell us a lot more than just standard petrographic microscopes. So in evaluating the extent of diagenesis, we categorized our samples in 3 different categories based on the features that were displayed. So here's an example of category 1 sample, and here is pretty homogeneous and is not much color variation and not much grain size distribution. So we can tell from this sample that it hasn't gone through many chemical or diagenic alterations, and it's pretty well preserved. In category 2, however, there are patches indicated by these circles of yellow mottling or diagenic alteration, we can assume. And this sample here that in these 2 sets of images are at 2 different sites, so at site 5 and site 10. And at site 10 is a very different picture, so there's not as much yellow luminescence or variation, and it's more homogeneous like the category 1 sample. So there are a few patches that can be well preserved, as well as a few diagenically altered patches. Now this is an example of category 3 sample. If you guys look at the images that are zoomed out here in the right corner, there's so much variation and so much yellow luminescence throughout the sample that it's really hard to isolate and pick out any homogeneous features. And also in the zoomed in picture here of the same sample, you can see there's some grain size variation. So there's coarser grains along this large detrital grain, and also there's smaller grains outlining that. So that tells us that there was some type of possible recrystallization or some type of alteration. So in categorizing these samples by diagenic alteration, we also came across a sample that gave us some insight into the source of diagenesis or what type of interaction these samples may have had. Here is a sample from a raptor section, and it's one sample taken in 2 different sites. And in the top picture here is a microspar lining of void space in the center here, indicated by the dark red. And here you can see between the microspar lining, which is this slightly lighter red, and the void space, there is a lining of yellow luminescence, yellow to orange luminescence, and you can kind of see that they look like they're in bands. So this suggests that there is some type of fluid that passed through the sample, through the void space, and caused alteration within the sample or caused secondary crystallization, and these bandings are those secondary crystals that are growing into the void space towards each other, trying to close into that void space. In the same sample but a different location, there was also a similar patch of spar in a reddish color, but this one is all filled in or doesn't have any void spaces, but you can still see linings of yellow luminescence, as you can see in between the spars in this top photo. So this also kind of gives us a hint that there was some type of fluid that passed over the sample and most likely dissolved many of the pre-existing grains that existed here to form this spar and recrystallize to form this spar. And this gives us insight that there was possibly some type of interaction, probably with groundwater in this sample. So in addition to looking at diagenesis, we also found a couple of samples that gave us insight to the types of environment that these samples developed in. And the two photos here are of one sample at two different sites. And what we found outlined by the black arrow here are ostracot shells. And in photo B, we found charophytes outlined by the white arrow. And those give us signs that they grew in a shallow or lacustrine environment and was most likely a pond or something like that. And in photo C, outlined by the black arrows, are these linings that are curved, and those are circumgranular cracks, and those give us insight that those developed in a Paleosol layer where there was clay involved and there was expansion and shrinkage of the soil. So after all of these analyses, I made a graph of all of the samples by stratigraphic unit. So Borchers section 4 is indicated by this stratigraphic unit over here and so on. And what I found was that there was generally a progression of diagenesis as we went towards the base of the stratigraphic unit. So Borchers 3 section is a really good example of how the samples towards the surface of the unit are not as diagenically altered as the base here. So I should start off with this. And in this graph, the red is category 1, the orange is category 2, and the yellow would be category 3. So as we go down into most of the layers, there is a progression of diagenesis, which would make sense because the older layers, which are now lower in the unit, are more subject to interacting with the groundwater level. So it's definitely logical, and it was interesting to see this all put together. I'm really excited about it. And so from all this information, we can conclude that although there are some samples that are altered, there are enough samples that have been preserved, or category 2 samples where we can isolate those homogeneous areas and use them as a true reflection of the Paleosol layer that the soil first formed in. Yeah, sorry. And also the category 3 samples that we did find, although we can't use them as a true reflection of the soil they formed in, we can use them as insight into what type of environments they did grow in and what types of diagenic effects were applied to them. And lastly, a more extensive study would be needed because this was only 22 out of the 56 samples that were taken for isotopic analyses, and there could be a larger story here or even more of a progression of diagenesis that we're not seeing. So definitely more studies would need to be done. And I'd just like to take a moment to thank Recess and my mentors, Katie and Karen, and the team at Meade Basin who allowed me to come aboard with them and do all their different tests because it's such a large group. And I actually had the chance to do a couple of modern rodent fauna surveying. So there I am holding a very cute and cooperative mouse there. And we were able to take samples of the modern rodent fauna for the project, and also all of the people who helped me at CU with interpreting and preparing the samples, and all of the supporters like NSS and ExxonMobil who made it possible for me to be here. Thank you.
Great job, Crystal.
Thank you.
We have time, I think, for one question.
That was a really nice job, really, really interesting stuff. Raises a lot of cool questions. I noticed in one of the images that you showed that you've got some fossil material in there too. And it looked to me like, you know, the ostracods and some of those bits were non-luminescent in comparison to the matrix. And I'm wondering if you think that maybe is there enough fossil material in there that you could actually do isotopic work on the fossils per se instead? Because you're more confident that maybe that's primary?
That would be interesting if we're able to isolate those ostracod shells. I actually, in that section, that section was actually only 2 samples from that section was taken. So it is possible that the rest of the thin sections from that sample would have much more ostracod shells, and it would definitely be really cool if we can look at those and isolate those. Yeah. Thank you.
All right. Next summer, yeah. All right. Thanks, Crystal.